Hello dear students. I am meeting you again in lecture number 2 on exact differential equations. I again tell you I am dedicating this lecture to undergraduate classes of different universities, and this video also goes to engineering BTech classes. If you want to watch this video, lecture number 2, it is necessary that you must watch first lecture number 1 on exact differential equations. What we did there, you will find that we are doing there the necessary and sufficient condition for m dx plus n dy to be exact. Necessary part we did. You have necessary part there. Now we have, it is converse part. Converse part, or you may also say it is a sufficient condition. Sufficient condition. We write here in sufficient condition, we show, or we first take this way. We write let m dx plus n dy is equal to 0. M is some function of x and y. N is also some function of x and y. Be such that, we are taking this for granted, be such that dou of m with respect to y is equal to dou of n with respect to x. You are taking this differential equation. You don't say at this time it is exact. You say that this differential equation is such that it satisfies this condition. Partial of m with respect to y is partial of n with respect to x. We will prove that with this condition we can express this m dx plus n dy as a differential, exact differential of some function. You see how we start. We write here in the proof, converse part of the proof, we assume, let us assume that integral of m dx, when we integrate m dx, actually what is m? M is some function of x and y. We integrate it with respect to x. Say it is u plus, it can be some constant. You may take, let it is c1, some constant. That means we are treating here y as constant. Integration is done with respect to x. When we integrate m with respect to x, we get some function, treating y here as constant. Say it is u plus c1. Let us name this. This implies, if we name this third, if we differentiate this partially, integral of m with respect to x, we integrate it partially. What is this? It will be partial of u with respect to x. C1, it is constant. It is a constant. We are treating y constant here, differentiating with respect to x. This will be 0. Now, this is the reciprocal of each other. You will get here, your m is a partial of u with respect to x, which implies if you differentiate this with respect to y, partial of m with respect to y is what? Partial of del u by del x with respect to y. This comes out to be partial of m with respect to y is dou 2u by dou y dou x. Dou 2u by dou y dou x. Well, but partial of m with respect to y is what? It is your del n by del x. So you can write that this setup implies that it is dou n by dou y is equal to del 2u by del y del x. Okay? So I have got here m is equal to, this I will need later on, this one, this equation, I will name it for the time being alpha. Let this equation be alpha. M is del dou u by dou x. I may need it in another setup. I will name it equation alpha. So when I differentiate this partially with respect to y, you will get this thing. I differentiate, it is del 2u by del y del x, but this is equal to this. So use it here by using second equation. Okay? So you have come to this. Let us see what happens then. You see, since dou 2u by dou x dou y is equal to dou 2u by dou y dou x. This is your dou 2u by dou y dou x, is it? This is equation number fourth. So what does fourth imply? So fourth implies, when we use this in fourth, that is del 2u by del u, del y del x, I will write, instead of this I will write this now. So fourth implies partial of n with respect to y will be equal to what? Dou 2u by dou x dou y. So we have got here it is del m by del y. It is actually here x. We have a mistake here because there we have dou m by dou y is equal to dou n by dou x. The condition is partial of m with respect to y is partial of n with respect to x. So given condition we take dou m by dou y is dou n by dou x. So we replace this by this. We have got here dou n by dou x. This is dou n by dou x. Okay? We took this condition. This you can write dou n by dou x is partial of dou u by dou y with respect to x. Okay? Now we integrate it, integrating with respect to x. When we integrate with respect to x, here we treating y what? Constant. We are treating y constant. When you integrate this with respect to x, this will be n is equal to, this is partial of u with respect to y, okay, plus some constant, say it is c. Here c is a constant and you took here y also constant. So y being also constant, there is no ambiguity. Without loss of generality we can say our y is, this is arbitrarily constant. This does not involve x, but y is our constant. So I will choose c is equal to some function of y. Remember, here this c is constant. It does not involve x. Y is our also constant. So I can choose c as some function of y. So I have got n is equal to dou u by dou y plus, instead of writing this c, it is some function of y. let this be beta. Remember here, phi of y does not involve x here, because our y is here pure constant in this setup. So when I take c is equal to phi of y, I take c is equal to phi of y, means that phi of y does not involve x. It is a constant here, as we do. This is beta. Alpha, you know what is alpha. Now you see how we proceed. You see how we go now. Now you have, I will take our own differential equation. Now, what is m dx plus n dy? What I have to prove actually? I have to prove that this m dx plus n dy can be expressed as the exact differential of some function. Then partial of m with respect to y is partial of n with respect to x. When we take dou m by dou y is equal to dou n by dou x. Well, so with this I have got alpha, where I have found out m, and this is your n. I will use the values alpha and beta. What was your alpha? You remember? Your alpha was, it was m is equal to partial of u with respect to x. This was your alpha. And n is partial of u with respect to y plus some function of y. It is a constant here. It is free from x. So you see, I will use it here. It is m, the value of m. It is dou u by dou x dx plus, use the value of n. It is your dou u by dou y plus phi of y into dy. Okay. Now distribute this. It is partial of u with respect to x dx plus partial of u with respect to y dy plus phi of y dy. Phi of y involves y. There we took it as constant. It does not involve x. It is phi of y dy. Now with phi of y, we have the derivative of y, that is dy. This you know what is this thing. This is your du. Okay. This is your plus phi of y dy. Now I can write, note this setup. Now phi of y dy, I can write this d of integral of phi of y dy. Because integral and derivative reciprocals of each other, you will again get this phi of y dy. Phi of y dy, d of integral of phi of y dy. Therefore, this is your du plus, instead of this, I will write this thing. It is d of integral of phi of y dy. So what is this? It is d of u plus integral of phi of y dy. Phi of y is now function of y that does not involve x, as per our assumption. There we took phi of y as a constant that is free from x. Okay, remember this. In any way, if I denote this by v, this will be d of v, where you took v, where your v is now u plus integral of phi of y dy. So what you have proved? You have proved that m dx plus n dy is an exact derivative of what? V. So we have proved. So we have proved that m dx plus n dy is what? D of v, exact derivative of v where your v is, it is u, remember this, u plus integral of phi of y dy, some function v. So what is this in by definition? M of dx plus n of dy could be expressed as the exact differential of some function. So by definition m dx plus n dy is equal to 0 is what? Is exact. It is the sufficient part. Previously in our previous lecture, if you want to go through this lecture number 2, lecture number 1 is very important, because there we did the necessary condition for m dx plus n dy to be exact. We there proved that if it is exact, then partial of m with respect to y is partial of n with respect to x. Okay, so conversely what we did if m dx plus n dy is equal to 0 is such that it satisfies partial of m with respect to y is partial of n with respect to x, del m by del y is del n by del x, then the m dx plus n dy is exact with this. Hence m dx plus n dy is equal to 0 is exact if and only if partial of m with respect to y is partial of n with respect to x. Partial derivative of m with respect to y is partial derivative of n with respect to x. Dou m by dou y is dou n by dou x. This is necessary assumption. I have already told you that for UG undergraduate classes, this terms forms the part of the students who are pursuing the undergraduate courses or integrated courses, 5-year integrated course. This term is there a part of syllabus. It is the part of syllabus. But for other students who are pursuing engineering class in engineering mathematics, BTech, extra, you have to just enjoy the proof, and this is necessary for you to apply this condition to verify this is exact. Then you have to find out solution. Now on the basis of this, I can give you the method of solution, how we solve the exact differential equation. But I will take sufficient condition. What we did in the sufficient condition, I will take this as the working rule for solving the this exact differential equation. This will help us to deduce the working rule for solving the exact differential equation. It is a very important theorem that we did in these lectures. After that, we will be having the application part. You see how we proceed now. This is your method of solution. Method of solution for m dx plus n dy is equal to 0. How we solve this, how we write the solution. Setup number first you have seen, this is equation number 1. You have setup number 1 is, first setup you have to check first if partial of m with respect to y is partial of n with respect to x. If we observe del m by del y is del n by del x, then equation first is exact. It is exact. It is exact. If it happens. When it happens, what is solution? Then step number 2 is, step number 2 you will see, when it is exact, this implies there exists some function in x and y such that, say, v, such that m dx plus n dy is total differential of v. What you took v there, if you remember, our v was there, it is u plus integral of phi of y dy, where this phi of y is free from x, as we took it in constant. Go to that alpha, the setup is before beta, this is the beta, this is beta, this this is u, it is the alpha. You go few steps back, you will see that this phi of y is a constant. We took it c, but it does not involve x in any way. This is 0 by first. It will be d of this u plus integral of phi of y dy. You can write this that we have got now method of solution. In method of solution, d of u plus integral of phi of y dy is 0. Now integrating both sides, say with respect to x. What is this? This will be u plus integral of phi of y dy is some constant c. But what was your u? From alpha you have partial of u is equal to u was there integral of m dx. Y was here constant. Replace this by this. It is integral of m dx plus integral of phi of y dy is equal to c. You again go to beta. What is phi of y? It is n is equal to phi of y plus c. What is phi of y? Phi of y involves those terms of n which do not involve x, phi of x. So in this case we write it is here y constant. It involves terms of, these are terms of n free from x. Those terms of n which are free from x. Hence we say, when m dx plus n dy is equal to 0 is exact. Now you have the condition for exact. Partial of m with respect to y is partial of n with respect to x. When it is exact, how we go with the solution? Solution is given by simple way. Solution is integral of m dx plus integral of n dy is equal to c. C is some constant. We treat here y is constant. We treat here y constant. And in this n, as far as this is concerned, phi of y dy, it does not involve x. From n we take terms. Here we have terms which are free from x. That is, in other words, we take from n those terms for this integral. From n we take those terms for integral which do not involve x, which are free from x. Then you have this method of solution. I have given you the method of solution. You have seen where from I have deduced this method of solution. It is the sufficient condition of the necessary and sufficient condition for del m, this m dx plus n dy is equal to 0 to be exact. The necessary condition we did in lecture number 1, and insufficient condition we did it here in this lecture, and there we have deduced the condition for this solution. It is a solution for m dx plus n dy is equal to 0. How we solve it? It is a solution. Now I will take the application part, how we apply this. Okay, how we apply some questions I will show you here, and you will do maximum questions from other books. You have so many books at your disposal on this exact differential equation. You do. I will take some questions. I have well, we have published our own book It is a book on differential equations. We published it in 2017 with O.P. Arora and me. This book, it is available in this is not available in our city because of change of syllabus. We had published it in 2017. It is a very interesting book, but it contains some topics which we don't have in here in JK, this syllabus. However, you will have this book in other north states of our country. I have some questions from this book. I will take some questions for application and you will do the questions accordingly. Okay. Let me have some questions here from this. I will take a question here. This is application on, this is the application part. Application part of exact differential equations. Let us have a question here. Number 1 minus 2xy minus y square dx minus x plus y square dy is equal to 0. This is first, you have to find solution. Because we are dealing at this time the exact part, let us have that. We will do it by exact method. How we proceed is, it is your m dx and dy, okay? You have m here, 1 minus 2xy minus y square, and you have n minus times whole square. What is partial of m with respect to y? It is minus 2x minus 2y. This you can write minus 2 times x plus y. What is partial of n with respect to x? It is also minus 2 down. It is x plus y. You observe that this is equal to this. Yes, you have partial of m with respect to y is dou of n with respect to x. Yes, equation first is exact. It is exact. So what is solution? Solution of this will be integral of m dx plus integral of n dy is equal to some constant c. Here you have to treat y what? Constant. Here you have to take to those terms of n which are free from x. Terms of n which are free from x. How you proceed then? You see, you will write this. This is integral of your n is 1 minus 2xy minus y square dx, then plus integral of, it is dy is equal to c. What is your n actually? Your n is minus times x plus y square. That means it is minus x square minus y square minus 2xy. We have to take here the terms which do not involve x. Which do not involve x. This involves x, I don't need it. This involves x, I will drop it. This does not involve x. So I will write here, it is what? It is your minus y square. Minus y square. Okay? This is integral of 1 dx, treating y constant, I have written here y constant, minus 2y, integral of x dx, minus y square is constant, integral of 1 dx, it is minus, integral of y square is y cubed by 3 is equal to c. Now let us simplify this. Okay. Indeed, this is x. This is x square by 2. It is minus yx square. This is minus xy square. This is minus y cube by 3 is equal to c. This can be the solution. It is the solution. So this is the exact, you know what does this actually represent by definition. That means our given differential equation is such that it is the derivative total differential of this. Okay, this is one application. Let me have another application. I will take one more application here. Let us have application here, one more. You have, say, suppose you have to solve the different equation ax plus hy plus g dx plus hx plus by plus f dy is equal to 0. It is ax plus hy plus g plus hx plus by plus f dy is 0. How you go? You have to first take it for exact test. Your m is here ax plus hy plus g. Here your n is hx plus by plus f. What is the partial of m with respect to y? It is your h. What is the partial of n with respect to x? It is also your h. So yes, you have partial of m with respect to y is partial of n with respect to x. So equation implies what? Equation first is what? It is exact. Equation first is exact. My first is this. When it is exact, what is its solution? It is integral of m dx integral of n dy is equal to c. Here y is constant. Here terms of n which are free from x, I have to write always whole m. M is your ax plus hy plus g dx. But in case of n, I have to drop those terms which involve x. Now in n, this involves x, free from x. We have to drop this, we have to write it. It is by plus f dy is equal to c. Now you can write the solution. The solution will be a integral of x dx, y is constant, h is constant, hy, integral of 1 dx, integral of sum is sum of integrals as you know, g, integral of 1 dx, plus b, integral of y dy, plus f, integral of 1 dy is equal to c. So you integrate this, it is a x square by 2 plus hy x plus gx plus b y square by 2 plus fy is equal to c. So this is the solution. This is the solution of this. You can write this as it is 1 by 2 ax square plus by square plus hxy plus gx plus fy is equal to c. You can take to multiply. This can be the answer. It is ax square plus by square plus 2hxy because it represents the curve plus 2gx plus 2fy is equal to 2c, that which you choose as c. So it is ax square plus by square plus 2gx plus 2fy plus 2gx plus 2fy is equal to c. That means the total differential of this, when we find out the total differential of this is, this will be the given differential equation. Okay, this is one more this example we did. It is application part we are doing. Okay, let me have one more application on this. We can have one more application. There are so many applications. I have picked some typical one. Let me take this application. Solve differential equation y into 1 plus 1 by x plus cos of y dx plus x plus log x. In fact, you can write this log in mod log x minus x sine y dy is equal to 0. Y into 1 plus 1 by x cos y dx plus x plus log x minus x sine y dy. You have this differential equation. You see, if it is exact, how we solve such differential equation. This is also a typical one. Because if you go to solve this differential equation by this variable separable method or by homogeneous, this seems to be difficult there, but exact may help it to solve very easily. Our m, we will take here coefficient of dx, it is y times 1 plus 1 by x plus cos y. Okay, then we have n, it is x plus log x minus x sine y. Here I have to find out partial of m with respect to y. It is 1. This is treated as multiple constant. It is 1 plus 1 by x. With respect to y, it is minus sine y. We are differentiating this partially with respect to y. Now here we differentiate this partially with respect to x. It is 1. It is 1 by x. It is 1 minus sine y. You see, this and this is same. So what does this mean? Partial of m with respect to y is partial of n with respect to x. So means equation first is exact. So when it is exact, you know the solution, how we go. We write the solution. It is integral of m dx plus integral of n dy is equal to c. I have already told you, in terms of m, in case of m, you write full m. You write m what it is, but treat y as constant. Here in this case, you drop those terms which involve x. You write the terms which are free from x. You see, this is m. We write what is m. M is our m is y times 1 plus 1 by x plus cos y. This is our dx integral of, look here, n. This is your n. Look here, n. This is my n. This is my n. I have to write down terms which are free from x. First term involves x, second term involves x, third term also involves x. So I can write this is 0 dy. I will not write this one. So this is only, you get this only. It is here constant, see, this can also be constant, because you say this integral of constant is 0. If you write here constant, that will be again a constant. This is your integration with respect to x. I will write here y, treat as constant, 1 plus 1 by x dx plus cos y integral of 1 dx is equal to c. Okay, this is y here. Integral of 1 with respect to x plus integral of log x, 1 by x with respect to x is, you know, log x plus cos y, it is out, cos y, then it is x is equal to c. This is your y times x plus log x plus x cos y is equal to c. It is the solution of this differential equation by exact method. Such differential equation is difficult to solve otherwise, variable, separable, so on and so forth. Let me have one more example. This is the application part that I am sharing with you. This is a problem which you come across in all the books. You solve such question in two ways. There are some questions I have already told you can solve with different methods. Suppose I take a question here. It is solve 1 plus e raised power x by y dx plus e raised power x by y 1 minus x by y dy is equal to 0. Okay, I have picked some peculiar question from this book. It is one of this. You can solve this differential equation by previous method, homogeneous method. How? You see it is x by y here, x by y. I can write it this way. It is dx by dy when you simplify this. Dx by dy will be e raised to power x by y, in fact minus 1 minus x by y by 1 plus e raised power x by y. I take this to that side, dy dx by dy, it is e raised minus times e raised power x by y, 1 minus x by y, 1 plus e raised power x by y. It is a homogeneous. Which homogeneous? It is a homogeneous of this part. Dx by dy is psi of x by y. It is a homogeneous. Now by that method you can also solve by homogeneous method. If you put here the substitution, you usually put x is equal to vy. X is equal to vy. You will get dx by dy is v plus y dv by dy. Okay, when you substitute here dx by dy here, you will replace it by v plus y dv by dy here, and you will replace x by vy. You will see it becomes invariable or separable problem. You can solve it by that method. You might have done it there. That means this is a differential equation. You can solve by the homogeneous method, and you can solve it. Let us see, can we solve the same? Is this a differential equation that can be solved by exact method? You see how our m is here 1 plus e raised power x by y. You take your n is here e raised power x by y 1 minus x by y. You see partial of m with respect to y is, it is 0. It is a exponential function. Exponential function as it is x by y, e raised power x by y. Then differentiation of x by y with respect to y. What is that? Yes, what is that? Derivative of x by y with respect to y. X is a multiple constant. Take it out. Derivative of 1 by y with respect to y, it is minus 1 by y square. So derivative of x by y with respect to y is minus x by y square. So you get it minus x by y square into e raised to power x by y. It is partial of m with respect to y. Clear? Remember, exponential function, it is 0. Exponential function as it is. Differentiation of power x by y with respect to y, treating x constant. Come now here. What is this? It is n is equal to e raised power x by y minus, this is x by y e raised to power x by y. We have to differentiate n with respect to x. Differentiate n with respect to x. How we go? This is the exponential. Differentiate this with respect to x. It is e raised to power x by y as it is, differentiation of x by y with respect to x is 1 by y, then minus, here this term, you can take 1 by y out, very important setup, 1 by y out, x into e raised power x by y, product rule, differentiate with respect to x. Derivative of x is 1, e raised power x by y as it is, then plus x as it is, derivative of x by y, e raised power x by y into 1 by y. Let us simplify this, what this gives. Let us simplify it. It is partial of n with respect to x I am finding out. It is 1 by y, e raised power x by y, then minus 1 by y, e raised power x by y. This and this is minus x by y square. When I multiply this with this, minus x by y square. What? E raised power x by y. This and this goes. This gets us partial of n with respect to x is minus x by y square into e raised power x by y. Oh yes, this is exact. Minus x by y square, minus x by y square, e raised power x by y. Here also minus x by y square, e raised power x by y. But here you have to be very cautious. Here my y is constant. I write 1 by y out. Then this, then derivative of here, I write here 1 by y out in this case. Then derivative of x e raised power x by y with respect to x. The first differentiation of this as this is, then x as the derivation of e raised power x by y with respect to y. This comes out equal. Now you can apply, you can use here you can write it a solution. It is exact now. You have proved partial of m with respect to y comes out to be partial of n with respect to x. So it is exact. So what is solution? It is integral of what it is, 1 plus e raised power x by y dx. Plus here terms which are free from x. If we take this, it involves x. This involves x. This is nothing. 0 dy is equal to c. Sometimes you write it as c. This is also some constant. This is some constant. It gives constant. So it is integral of 1 dx plus integral of e raised power x by y dx is equal to c. Clear? So this is x plus this is e raised power x by y with respect to x. It is derivative in the numerator. It is 1 by y is equal to c. This is x plus y e raised power x by y is equal to c. This is the solution. You can write sometimes this solution be as y times x by y plus e raised power x by y is equal to c. I took y here common, so this gets divided by y, x by y, e raised power x by y is equal to c. This is something that I have given you for this application of this. And the differential equation, I have given today's lecture the sufficient condition for a differential equation to be exact. Then from the sufficient condition, I have deduced the condition of this differential equation solution, how to solve the differential equation by this method. That's the method of solution, working rule that I have given. Then some examples, typical examples, how we can solve the differential equation when it is exact, how we give it is solution. I think this is the sufficient application part. Now in next video, we will be showing you sometimes the differential equation is not exact. We want to reduce it in the exact form. That is known as differential equation is reducible to exact form. Reducible to exact form, or differential equations that can be bring into exact form by integrating factors. There we need integrating factors. There are in fact 4 or 5 rules of integrating factors. I will also share those rules with you. That will be, I may need one or two these lectures more on exact differential equations. I hope you have understood this all, and thank you very much, and till then you take care and revise the things for. Thank you very much. Okay.